Are you ready to go? Recitation. Okay, so this week we're talking about basically when I took the class right when the pandemic started. So this stuff is a little bit more muddy for me um, compared to everything else in Orgo 2. I'm going to continue to kind of do that thing where I denote electrophiles with like yellow highlighter and nucleophiles with blue highlighter. So like, blue is like I think of like electrons and yellow is like electron deficiency. Anyway, so we're starting off with this first one, just asking us to draw the enolate ion. Hopefully you guys are comfortable with that. And so then just draw the resonance for it. And so for this first part, I technically drew the ketone attacking um, the hydrogen. That's not really what would happen. It would be more of, there's more likely to be like a base that would pluck it. And then, oxygen would pluck it away from the base. But, for simplicity, that's resonance structure for that compound. This one's going to be more like an SN2 reaction. And so when you're thinking about SN1 and SN2, SN1 happens because you have a really strong electrophile. So like, and it's strong enough so much so that like you actually have an intermediate cation that is a lot of times like stabilized. Um, SN2, on the other hand, is based on a strong nucleophile. So it's when you've got a lot of negative charge buildup. And so you could actually look at those as two different, again, like sides of the pendulum, just like with acidity, comparing acidity and all of those types of like concepts. Um, because, lower acidity, lower pH is more acidic, which means there's more protons, which means that there's more positive in the solution. And so you're going to have a solution that's, for example, really prefers SN1. And so SN1, remember, is actually works really well in protic solutions because all of those little protons are bouncing around in the solution, and they kind of like you could say they normalize the positive charge on the cation. Um, anyway, all you need to know for this, what was it? What was the problem? What was the problem asking again? I got lost in wanting to talk about it. Um, yeah, I drew the intermediate here and how this reaction happened, just so you guys can still like familiarize yourself with how to form these beta keto esters. Um, one is going to form the nucleophilic side. The other one is going to form the electrophilic side. And then when they attack, you get this same intermediate that we've been having with aldol. If you'll remember with aldol, this formed like a positive and this formed like an alcohol. And so like, yeah. And then we had this eventually just like alcohol leaving. Um, and when it left, it formed like I forgot exactly. That doesn't mess that I messed that up. What you need to know is common theme is this tetrahedral. I have not studied like I should clearly, um, but you've got the existence of this electrophile, nucleophile, and tetrahedral intermediate. And for Claisman, Diekman, and Aldol, they all look similar and know how those work. Yeah, the ethanol is going to leave as a leaving group to the ester. And then when it says this last one, consider where like the new double bond is. Remember that you need to know that this is a nucleophilic carbon, and so those are going to be very reactive. And so, for example, what's the new bond? This stuff out here is going to be fairly inert compared to what's going on in this carbon, and that's because you've got resonance that's going on all the way up here, down, and all the way back up here. So electrons are flowing all through that area as long as they can pop off a proton. As long as this proton is gone, something can take away that proton. It creates a huge pi system, and it's very favorable. And that's why when you're ending these reactions, you're going to want to use an acid at the very, very end because it locks that proton there, which keeps this bad boy from getting all reactive again. Um, keeps this promiscuous carbon from getting around. Yeah, that's that. So once again, oh gosh, nucleophilic carbons, electrophilic carbons are denoted down here. Yeah, that's that. Down here we've got, it's asking us to do Dieckmann. Dieckmann is just like Claisen, but it's intramolecular. And so I like these a lot. They're kind of cool. And all you have to do is just draw your numbers, and then it's like, it's that simple. So this is perfectly symmetrical, so it doesn't matter which side you pick. It's going to go inside, and then it's going to, once you've numbered it out, voila. Once again, here is that four substituent tetrahedral intermediate. For this one, what's going to happen is this alcohol group is going to leave, and basically this like oxygen group is going to come down with its electrons and form a ketone. And so yeah, you get this ester group, keto beta ester. Did I say that right? I think I did. Any questions on all that? Pretty straightforward. Cool. Moving on down, we've got once again more beta keto ester formation. Once again, I have denoted nucleophile, electrophile, and then I also went ahead and I like to, like, for these, recognize when I've got stuff that is past this nucleophile. So like if there's anything that's not a hydrogen connected here, then I like to put a number on it because it's going to be attached to the nucleophilic carbon at the end. And so, yeah, that's what that A represents. It also just helps with bookkeeping. Once you've done that, you're going to do your normal like esterification. This one's kind of reverse. So by adding acid and water, it allows this ethanol group to leave, and you're going to get left with just a beta keto carboxylic acid. And so then you can, this is where you get like how THC is made in your body, or actually it's how you, when you burn it, you're burning off the CO2. And so what happens is when you increase temperature, this molecule right here is much more likely to basically go into a certain conformation where it is a perfect little like circle. And it's really cool because like these are all molecules that are like straight, like, you know, not necessarily planar, but they're just jig-jagged around. But if they all link in this perfect circle for a split second, the electrons from the alcohol will fall into towards this carbon here to make CO2. The electrons that were on the CO2 carbon go back to the original like parent molecule here. And then actually the molecule from this parent is going to punch off and steal the proton away from the alcohol group. All that to say, you get left with CO2 and then a ketone. But that ketone can tautomerize or whatever back and forth between these two intermediates. So it's real world chemistry, man. Any questions on any of that? Cool. So at this point, these are the group assignments. I'm going to stop the recording.